C2000 F28379D. So here I have taken an example of a buck converter with the specifications Vg is 20 and V0 is 8 volts. L and C are being designed to get a 1% ripple on your output voltage and 10% ripple on the load current, and the switching frequency is 50 kilohertz, and for the required specifications the duty is 0.4, right, and then the V reference is set to 3. The sensor gain is 0.375. So, the set control objectives is to achieve a gain crossover frequency of 5 kilohertz and a phase margin of 52 degrees. So, as we have seen in the earlier sessions, so the first step is to establish the control block diagram with respect to the control scheme. So, let us say here I am following an voltage mode control technique, and so I will establish the control in analog domain, right. So, where this becomes my V reference, which is 3 volts here, and then we have the V feedback, right. So, I have the converter model which is GVD of S giving me the output voltage V0 of t, taking D of t as an input. So, I have taken feedback, and the feedback gain is what is H of S, and of course, we know H of S into capital V0 will be equal to V feedback, which is nothing but V reference. So, H of S is found to be V reference divided by V0, and what is V reference? V reference is 3, V0 is 8 volts. H of S turns out to be 0.3750, and of course, we get the error and then pass it through the compensator, and of course the PWM, which is 1 by Vm, and this will be GC of S. So, maybe we can put everything in S domain, V0 hat of S, right. So, this becomes the control block diagram in analog implementation. Right. So, with this how do we start? So, as I have told you, we will start with the uncompensated loop gain Tu of S, which is defined with Gc of S being set to 1, and then analyze that system, and based on that we will go for the desired compensators, right. So, this is the uncompensated loop gain, what you see, which is Tu of S. Tu of S plot. I have taken here Vm is equal to 1. What is Tu of S? So, as we know, Tu of S is given by GVD of S into H of S and 1 by Vm, right. So, however, I have taken Vm as 1. So, with this, this is the plot what we are getting, where I am able to get a phase margin, I mean the desired gain crossover frequency is 5 kilohertz as we have seen. So, at 5 kilohertz, if you see here, I am getting a phase margin of just 2 degrees, however, which is not sufficient, right. So, accordingly, we need to do a compensator for the desired phase margin at the desired gain crossover frequency. But once we take this design, now once we do a digital controller design, right, the blocks as we have understood, we will be now seeing what all we will be seeing. So, once I take the same control into a digital platform, so maybe I will just write a digital So, if I go for a digital implementation, the everything of course is in digital. So, V reference and then I have here I have my plant model which is the same GVD of S, right, and then I take a feedback by using H of S. So, all this will remain the same, but however, we have certain additional blocks which is basically the data acquisition module which is performing the sampling and the conversion, that is ADC. So, here is where I get V naught of K I can write, which is a digital signal, and according to that I get my error being computed, and that's been passed to a digital compensator. I'll call it a GC of Z, and then we have the digital pulse width modulator which is DPW. Yeah, right. So, I get the output D of K corresponding to your VC of K, which is the output of the compensator. So, this becomes the control block diagram for the analog for the digital implementation, and once we implement the same in digital, so however the technique what we will be using is, after establishing the control block diagram, so we will be following the emulation based design technique. The design in the continuous time domain, however, shall be done by using the frequency response characteristics, and the compensators are designed to achieve the set control objectives. Now, the control block diagram in digital is established, and then you analyze the the uncompensated loop gain in digital, what I will call it as digital domain. TU of S, right, will be now having the same GVD of S, but then it has also the H of S, and then the GDPWM, and also G the characteristics of the ADC, right. So, with all this what we see here is there will be a phase lag or a control loop delay observed in your plot, right. So, that is being introduced due to the ADC and the DPWM module, and we see that there is a phase lag of 15 to 20 degrees observed. So, from minus 178 it's observed now the phase is minus 196, and however, this delay has to be now taken into consideration while doing the compensator and then doing a digital control implementation. So, here it is observed that at 5 kilohertz, which is the desired gain crossover frequency, a phase margin of 2 degrees is observed in my continuous time domain, but once I take it to a digital domain, a phase margin of only minus 16 degrees is observed, which is giving us a lag of 18 degrees. That is because of your delay introduced by the DPWM and the ADC module. So, now compensators are to be designed taking this phase lag into considerations. See, the optite model and the control design is validated in a hardware prototype for a digitally controlled buck converter. So, this is the
electric model or something.
Digitally controlled buck converter prototype. So, this is a digitally controlled buck converter prototype built for the same specifications and tested. So, here the controller used is F28379D, right, and the buck converter is designed for these specifications, and in this session we shall try to understand the controller implementations in digital domain and validation of the designed compensators using the software frequency response analysis tool or the SFRA tool of F28379D. So, this is the controller, this is the buck converter switches, and this 4 is your filter components what is being placed, right, and of course, this is a load rheostat. So, the if you see here the red plot gives the analytical uncompensated loop gain in continuous time domain. So, this is the red plot which is Tu of S in analog domain, right, which will be GVD of S into H of S into 1 by V. So, now with the in the digital domain when I am doing, I will consider my compensator I mean GC of S to be equal to 1, and the uncompensated loop gain is measured using the software frequency response analysis tool for the converter what was shown in the earlier slide, and this is what is being observed in this blue plot. So, the blue plot is measured uncompensated loop gain for a digitally controlled buck converter. Of course, the specifications are same as this, and this is the hardware prototype what is used, right. And then so this blue color plot is a measured plot when the converter is in operation. So, here if you see the phase plot, so we observe that the red plot is what is our continuous time domain, right, and then the blue is the measured for that digitally controlled converter, and you observe that there is a phase lag at 5 kilohertz, and then the phase lag is observed to be equal to 18 degrees, and this is what we observed in our earlier slide also. Phase lag of 18 degrees is observed between a continuous time domain uncompensated loop gain and then the same implemented in digital considering the delay model for GDPWR, right. So, with that the same is observed in the hardware implementation also, and these measurements and validation of course enables us to model the plant accurately and then do an accurate controller design. So, to obtain the frequency response characteristics, something like this what we are seeing in this picture, to obtain this frequency response characteristics, one could use an instrument which is the frequency response analyzer, right. So, that is one way. So, the other way of this kind of validation is by using the SFRA tool which is an inbuilt feature in F28379D. So, this SFRA is actually a software frequency response analyzer library which enables frequency response analysis on a digitally controlled power converter using the software. So, there is a user guide on this using the SFRA tool. So, you can refer to this manual. I think if you go through this manual more, you will be able to explore this tool, and I am sure you will be able to figure out more and when you start using it. Please go through the manual for complete programming in this, however, the complete programming may not be provided in this presentation. I am giving you an introduction to get to know that this feature is present in DSP and how it will be useful to get the frequency response characteristics and what can you do out of this tool. So, basically as I told you, this tool is helpful in doing the validation of the controller design. So, first of all, for installation of the SFRA tool in F28379D, you can refer to this user manual which gives you the steps. Just follow the steps and you will be able to do the complete installation. And then it also gives you an understanding and developing the code for SFRA. However, we will be just giving you an introduction about the feature of this SFRA and not getting into the coding part of it. So, this manual will give you the entire the development of the coding, and we shall see today what are the features and what one can do with this tool. So, basically as I told you, this tool is an inbuilt library of F28379D, and it operates using the SFRA _inject which is an inbuilt defined function inbuilt to give the perturbations of varying frequency as you set in your graphical user interface. We will see that in our next slides. So, here if you see, just to understand the basic operation, so basically this tool give let us assume that you have a signal V, right, and for that this tool will add a V cap, right, and this V cap is getting added to the signal V, and then eventually I get an output R, where R is nothing but V plus V cap, right. And what is this V cap? V cap, you can presume it to be something like V sin omega t. However, what will be the magnitude of this V? This V will be just 3 to 4% of your signal, capital V, and then this becomes your injection amplitude. Now, let us assume I need a model of this block G of S. So, I need to give this R as an input to this block, right, and the output will be now the Y, and what will be Y? Y again will be now having capital Y plus Y cap, right. So, the small signal model will be now G of S is equal to Y cap divided by V cap, right. So, the small signal model G of S will be now given by the Laplace transform of the output, which is Y cap of S divided by V cap of S. So, this tool basically enables us to get the ratio of the Laplace transform of the output to the Laplace transform of the input, which essentially gives me the model of the plant. So, it is injecting the disturbance V cap of varying frequency and thereby enabling us to get the frequency response characteristics or the model of the targeted plant, right. So, with this as the basic operation, after the installation of the SFRA, you will be seeing the setting of the graphical user interface of the SFRA tool. So, we will get a window something like this, right, where you can set the following. So, the first one is select the math mode, where you will be selecting this floating point, and then we have a setup connection here. So, basically it is for setting up the connection between the GUI and the DSP. So, this is done by setting the COM port. However, after connecting the F28379D, you can check the device manager accordingly, set this COM1 or COM2, whatever is being showing in your systems, and then based on the serial communication interface which is used in this, the baud rate is set to 57,600 bits per second. So, these are the preliminary configurations of the GUI of SFRA tool. So, with this we are ready for connecting. So, let us say if I say connect. So, now with this button being clicked, and SCI is getting established between the GUI and the DSP. So, the next settings followed is to get the model of the plant under considerations. There are two options. One is the plant mode. So, this is the selecting the mode. One is the plant mode and other one is the open loop mode. So, basically the plant mode is the Bode of the Bode plot for just the plant under consideration. So, this is only for just the plant under consideration. And open loop is for actually the cascaded transfer functions, cascaded blocks. So, this will be for example plant and the compensator. So, after this is what you set the start frequency, right, where you need to get the plot for. So, in this case we have set it to 10 hertz if you see here, and then the next is setting up the steps per decade. So, start frequency is 10 hertz, and then per decade how much is the number of steps. So, here we have set again 25 steps per decade. So, it will compute the magnitude and phase at a rate of 25 steps in one decade. It will compute your magnitudes and phase, and we have set the frequency length at the of 100. So, with 25 steps per decade, the maximum frequency what it will go will be, we will have 4 such. So, this will be the first 25 steps, second 25, fourth, third 25 and fourth. So, which will result my maximum frequency to be equal to 100 kilohertz. So, this is what will get reflected in your GUI, and the injection amplitude also you can set, and I have set here 3% of the steady state value. So, with this as our final settings in the GUI. So, you can now now set ready for injecting the perturbations at the desired point. So, you can click this start sweep. So, this will in fact activate the small signal perturbations or the injections. So, here as per the set configurations what we have done in our earlier slides, the perturbations will be varying from 10 hertz to 100 kilohertz, and the magnitude of the perturbation will be 3% of your steady state value. Right. So, with this now let us see some examples of the transfer functions, of the known transfer functions. So, we just started out with an integrator. For example, g of s is equal to 1000 by s, and this is an integrator, and we know that the corner frequency will be set to 159 hertz for this, and that is what we are seeing here, right. So, this SFRA results for the integrator is shown, and a corner frequency of 159.8 hertz is observed in this figure with a phase of minus 90 degrees. So, similarly, we have done it for lag compensator, which is Kp is equal to 1, and again Ki we have set it to 789.6 by 789.6. So, here we have considered a lag compensator with Kp is equal to 1 and Ki is 789.6. So, this is what is being considered as G of s is Kp plus Ki by s, and then the SFRA results for the same is observed in the GUI for the given values of Kp at Ki. So, with this as an introduction to the SFRA tool, so we have used this tool, and the uncompensated loop gain plot in a digitally controlled converter is measured using this SFRA tool, and the results are as shown. This is what we saw in our earlier slide, and we observed that the phase margin is now just minus 18 degrees, which is really not an acceptable one. And what was our set control objective, which is 52 degrees at the with a gain crossover frequency of 5 kilohertz, right. So, at 5 kilohertz I am seeing minus 21.6 dB as the magnitude and a phase margin of minus 18 degrees. So, with these two as obtained from the plant, that is your uncompensated loop gain plot, I will be able to design the compensators accordingly and get that set control objectives. So, this blue one is what we have measured in the hardware digitally controlled buck converter using the SFRA tool. So, once we get the measured plot, right. So, we will be able to estimate this is the current phase margin, just minus 18 degrees, and accordingly take that into consideration and do a design following the method of emulation based design technique, and of course implemented using the difference equation. So, the compensator I have just we have just gone through here the same in our earlier slides, earlier sessions. We have just seen this in our earlier sessions also. So, the crossover frequency is the desired crossover frequency is 5 kilohertz with a desired phase margin of 52 degrees, right. So, with this so this is the set control objectives. right. And the lead compensators are designed for a phase of 70 degrees in order to achieve the phase margin of 52 degrees at 5 kilohertz, and you get your FZ and FP. So, your lead compensator GC lead of S is equal to the gain GCO plus 1 plus S by 2 pi into FZ divided by 1 plus S by 2 pi times FP. So, this forms my lead compensator. FZ and FP are selected using this for a phase of 70 degrees as we see here, in order to achieve 52 degrees as my phase margin at 5 kilohertz, right. So, with these two being done, I will be able to get the gain of the compensators, gain which is GCO, to be provided by the lead compensator, and we have already seen that the uncompensated loop gain is having a minus 21 dB gain at the 5 kilohertz, right. And so, in order to make my gain crossover frequency to be 5 kilohertz, a gain of plus 21 dB should be provided by the lead compensator, correct. So, that shift is getting provided by the lead compensator, and thereby I get my GCO to be equal to 1.98. So, with this my compensator is designed to be 1.98 into 1 plus S by 2 pi times 0.881 K whole divided by 1 plus S divided by 2 pi times 28.356 K. So, this becomes my lead compensator. So, this designed lead compensator is what is modeled in MATLAB, and we get this kind of a plot, and this being multiplied by your uncompensated loop gain into G lead is ensuring a phase margin of 52 degrees, right, at 5 kilohertz, and the gain crossover frequency is also now made to 5 kilohertz. So, this has been validated in the digital implementation. So, the compensator, so the designed compensator is implemented in MATLAB, and the plots are shown here. See, the compensator loop gain with the, that is the uncompensated loop gain with the lead compensator is shown in this plot, which will give us a phase margin of 52 degrees and a gain crossover frequency of 5 kilohertz, right. So, the validation of the same is being done using the SFRA tool, which will be shown in the upcoming slides. So, if you see here, this is the lead compensator, which is implemented by using the discrete equivalent and the difference equation. So, this difference equation is implemented in the DSP, and the designed compensator is implemented for the digitally controlled buck converter. So, this is the compensator what has been designed and implemented in the measured using the SFRA tool. So, this is the measured compensator using the SFRA tool. So, what we have seen is to get the desired performance in the high frequency region, a lead compensator has been designed, and the same has been measured plots are being observed in the using the SFRA tool. And now, to obtain the high gain in the low frequency region, we have used a lag compensator, and however, the lag compensator is designed to be GPI, which is S plus omega L divided by S, which can also be written as 1 plus. So, the GPI of S is S plus omega L by S, and the compensator is designed at a frequency of 1/10 or 1/20th of your natural frequency response of the converter, which is 1 by root LC, and in this case it is around 400 hertz, right. So, 1 by 2 pi root LC, which will be equal to 400 hertz. So, 1/20th, which will be 20 hertz, is what the lag compensator is placed at, so as to not having an impact in the high frequency performance. right. The designed lag compensator is verified in the SFRA tool, again using the test-ins method and then implementing with a difference equation, and designed compensators are validated using in the SFRA tool. So, this is the measured plot using the SFRA. So, this shows the combination of, that is your GC of S, which is a combination of lag compensator into the lead compensator. Again, the blue plot is the one measured using SFRA, and then the red plot is the continuous time domain, I mean in the MATLAB, the model of the lag lead compensators has been shown here, right. And the implementation in difference using the difference equation and the test is discrete equivalent method will give us the plot which has been measured in SFRA. So, this is the compensator plots what has been designed for the digitally controlled buck converter, and finally we get into the loop gain characteristics, which is the compensated loop gain characteristics. Of course, the the red plot what you are seeing here is the analytical plot, but it is a compensated plot. So, I will call it as TC of S, which has been obtained by G VD of S into H of S into 1 over 1 plus ST by 2 into this compensator, and the blue plot is the measured one using the SFRA. Right. And so, what we observe here is there is a good match in the DC gain and in the natural response of the converter also, which is around 400 hertz. That is also observed where there is a double pole, and as a result of which there is a sharp change in the phase. But however, in my hardware implementations we see a little smoother change due to the track resistances and the resistances of your components, right. And as a result of which a lower Q is observed in the experimental plot as compared to your analytical one, right. So, and with the designed compensators, it is also observed that you are able to get a gain crossover frequency of 5 kilohertz and a phase margin of 52 degrees, right. So, with this we come to the end of the session. So, what we have learned in this session basically is there is a feature in F28379D called SFRA tool, which helps one to obtain or which enables us to obtain the frequency response characteristics, which will help us in obtaining the model of the plant under operation, right. And then we have also gone through the same using the example of a digitally controlled buck converter. Thank you.